Okay, here's a question on electrons in orbit about an atom. And we're going to look at how we consider those electrons in terms of their orbits, their shells, and their electric potential. So it says here, first of all, a very simple model of a one electron atom in hydrogen. This bound electron is confined to move in a straight line length A. So really, if it were a straight line, then what you have here is you have this system which is bound like a box. So it says sketch two possible modes of the standing wave. So this is just a simple length L. It is a bound electron moving, and its wave motion always makes standing wave patterns. So what is the first two possible modes of vibration? Well, the first one, if it were a standing wave, would look something like this. And the next one, if it were a standing wave, would look something like that. Good, so I think that's the answer to the first one. Show that the allowed values of the momentum are given by is an integer. Well, we know that momentum is h over lambda. That's the de Broglie relationship, which is stated up at the top here. And what we ought to say to ourselves is, what is the wavelength of this one? The wavelength of the first one compared to the second one. The wavelength of the first one, so for n equals 1, we have lambda is going to be twice the distance, because if that's half a wavelength, a full one, of course. And when n equals 2, lambda is going to be equal to a. So really, as we increase n, the lambda is decreasing, the wavelength is decreasing. So therefore, if we plug the equation into here, we can see to ourselves that the relationship is going to be the first one, so it's going to be 2 lambda over n. That makes sense. So if we substitute that back into there, sorry, 2a over n. So when we substitute that back into there, we have nh over 2a, which makes that proved correct. Hence obtain, so the next part, hence obtain an expression for the allowed values of En of the electron, energy of the electron, giving your answers in terms of. Okay, so the energy required is, let's think about this. Let's say that the energy, so this is part 3. No, I'm going to actually do part 3 on another bit of paper. So the energy is p squared over 2m. You might ask, where on earth did that come from? Well, it's the idea that you have momentum mv, and I'm trying to change this momentum into a kinetic energy, which is a half mv squared. But in order to have squared this function, I need to divide through by m, so that's giving me p squared over 2m. And therefore, what does that give me? Well, I now know that, obviously, my expression for P is NH over 2A. So therefore, P squared is going to be N squared H squared over 4A squared by 1 over 2M, giving me N squared H squared over 8M A squared. So there's an expression in terms of N, in terms of H, in terms of A, and in terms of course, this is the mass of the electron, I should say. Good. There it is. Now part 4 asks for taking A to be the approximate diameter of hydrogen. Draw an energy level diagram showing the 4 lowest energies of this atom model, labeling each with its energy. Okay, an energy level diagram. I think it's looking for something which is going to be showing us the energy. And then we just have levels associated with it. So for n equals 2, if I plug the number into my equation, no, let's start with n equals 1 first. Hold on, so hold on. N equals, the first energy level is going to be 1 squared h squared over 8mea squared. And when I plug those numbers in, that gives me, it's going to be a bit cramped, but here we go, 6.64 times 10 to the minus 34 squared over 8 by 9.11 times 10 to the minus 31 by 1.1 times 10 to the 10 squared. You can just see that, I hope. And that gives me an energy of 4.95 times 10 to the minus 18 joules. Okay, energy of number 2 is going to be 2 squared the energy of 1, which gives me 19.8 times 10 to the minus 18 joules. Energy 3 is going to be 3 squared energy of 1, which gives me 9 lots of it, 45.5 times 10 to the minus 18 joules. And of course, energy of 4 is going to be 4 squared lots of energy 1, which is 79.1 times 10 to the minus 18 joules. So they're all 10 to the minus 18. Let's put times 10 to the minus 18 joules in there. So I'm looking for 4, 19, 44, 79. So I suppose that's going to go 4, and the same gap to get 19 is 4 lots of that. Same gap, 44. 79 is going to be somewhere up there. With their associated energy levels. What's this? 4.95. 19.8, 44.5, and 79.1 joules. Good. What's the wavelength of a photon emitted when it moves from one model to the next in that state? Okay, so part 5 is then asking, the change in energy is going to give rise to a photon of energy or even of wavelength. So therefore my change in energy in this instance is asking for n equals 2 state to n equals 1 state. So I'm going to go from n equals 2 to n equals 1. I'm going to go from there to there. What's going to be the change in energy? Well, that gives rise to, then I have 19.8 minus 4.95 times 10 to the minus 18. That gives rise to 6.63 times 10 to minus 34, 3 times 10 to the 8 divided by my wavelength. And when I, therefore, my wavelength, when you plug that in, gives rise to 1.33 times 10 to the minus 8 meters, which is about 13.3 nanometers. What's that going to be? What spectral region does that lie within? Well, it's very ultraviolet. If we know that light, we have 400 to 700 nanometers is visible. Anything below is UV, and anything above is infrared. This is ultraviolet, very definitely. Okay, now starts, well, and that's very odd, isn't it? Because if you think about that, it's not going to be incredibly UV to that extent, and this looks rather large. There must be another model that works for this. So therefore, it's simply asking here that if you have an improved model of the hydrogen atom in which you have electrons in orbital shells that do something like this, rather than a straight line, maybe that gives a better condition for the situation. So it says, show the condition of either the angular momentum of the electron to be. Okay, angular momentum is merely the momentum times the distance you are away. And what we've got going on here is we're saying that the circumference of an orbit is going to be a whole number of wavelengths in order for that to take place. So therefore r is going to be n lambda over 2 pi. Of course, L is going to be momentum times V, which is mvr. And of course, my momentum is h over lambda given by de Broglie. So I should really say hr over lambda. So once I substitute this into here, that gives me an expression for h over lambda by n lambda over 2 pi, get rid of those, nh over 2 pi. So my angular momentum is a whole number of this constant, which is Bohr's condition for how he worked out the orbital positions of electrons. Good. Now it asks me to work out the total energy of the system. And what I need to do here now is I need to use exactly what I did before, whereby I'm going to say that the kinetic energy of my system, which is p squared over 2m, which is the same as L squared over 2mr squared, because of course L has this, it's the same but with r in it. And then I need to substitute my expression into there, which gives me L squared is n squared h squared over 4 pi squared 2m r squared. Let's make that neater. N squared h squared over, well, if you want, 8 pi squared m electron squared. Okay, we're not quite done there because that's just the kinetic energy. However, we know there's a potential energy associated with it, and the electrical potential energy is going to be 1 over 4 pi E naught Q1 Q2 over R. And I know that the charges, this is the charge of an electron, because it's hydrogen, that's the charge of the proton, the positive charge of electrons. That gives me E squared over 4 pi E naught R. Therefore, an addition of the 2, let me just get an addition of the 2, so this is part D. I have, sorry about the bell noise, so the electrical potential, total energy is merely an addition of the 2. And bearing in mind one of those charges was positive and the other one was negative, giving us a negative there. I mean, I have h squared, n squared, h squared over 8 pi squared m(e)r squared minus e squared over 4 pi e naught r. I'd say that is an agreement with that. So the last bit is now assume the actual radius. So the actual radius of the lowest energy state is the first one. Let's say this is n equals 1. So how do we make r at a minimum? Find the numerical value of r compared to that of a above. Okay, so how do we make it a minimum? So my total energy, and I want to work out when this function becomes a minimum. So what I want to do is say take dE by dr and then work out when it becomes a minimum equal to 0. I don't know why I did a line there. Okay, simply, so that's d by dr of n squared h squared over 8 pi squared mer squared minus e squared over 4 pi e naught r. So very simply, what happens here? Well, I get, this is minus 2, so minus 2 n squared h squared over 8 pi squared mer to the 3 plus, because I get a minus 1 down, e squared 4 e naught r squared. And when it equals 0, there must be the equal to each other. 8 pi squared mer cubed equals e squared over 4 e naught r squared. Therefore, r is going to be e naught h squared over pi e squared me. That gets rid of that, of course. that goes to 4. Get rid of the 4, etc., etc. That boils down to that. And then if I plug in the values E0, which is 8.85 times 10 to the minus 12, by 6.63 times 10 to the minus 34 squared, divided by pi, 1.6 times 10 to the minus 19, square it up by mass of the electron 9.11 times 10 to the minus 31, gives me 5.3 times 10 to the minus 11 meters. And of course that's the radius of my orbit, so therefore the diameter is going to be 2 lots of 5.3 times 10 to the minus 11, which gives me 1.06 times 10 to the minus 10 meters, which is pretty much 1.110 to the minus 10 meters. So therefore they add up, they make sense. Right, hope that made sense.